Good evening, everyone. Uh, I hope I'm audible. Uh, can anyone just confirm? Okay. Myself, Harish, I am a PhD student at ISER Mohali, and I will be taking these live instruction sessions for the course Introduction to Group Theory. Uh, our timing will be same, Tuesday, 6 to 8. So we can start with some doubts from the lecture notes. If you have any doubts, then you can ask. Otherwise, we will be discussing some problem sessions, some problem questions. So I hope my screen is visible. If you have any doubt from the lecture notes, then please let me know. We can first discuss that, and then we can go to some sample problems. Shall I assume that there are no doubts from the lecture notes? If yes, then maybe we can discuss the practice assignment. So this is the first question from the practice assignment, and so it's better if we have a two-way interaction. So you can share your comments, or if you want to solve the problem, then you can also give hints so that we can solve it together. So the first question ask about in which of the following cases H is a subgroup of G. So the first example is when G is the group of integers with addition, and H is the set of even integers. So what do you think? Is it a subgroup of G or no?
Yes, sir.
I can't hear.
H is a subgroup.
Yes, so H is a subgroup. Why is it so?
So, sum of two even integers is also an even integer. So it's closed.
It's closed. Very good.
And the identity exists, which is 0. And
Okay.
for every even integer, there exists an inverse, which is also even. So this is within H. So this is a subgroup.
Right. So, and in the lecture notes, we have already seen that all the uh, subgroups of Z are of the type NZ, right? Where N is a natural number. So here H is just 2Z, right? So that is also one explanation, but let's not use anything. Let's start from the scratch. So I think it was Angel, right? Pranjana. So as Pranjana said, uh, first of all, H is closed under addition, and also the identity 0, which is the identity element. This is also inside H, and for each element, say n belongs to H, there exists minus n belongs to H such that n has this minus n as its inverse. So it satisfies all the three necessary properties that are required for a subset to be a subgroup. And thus H is a subgroup of G. Good. So we can move to the second one. GLNC is the group of invertible n cross n matrices with complex entries, and H is a subgroup of GLNC in which instead of having elements from C, we are considering elements from Q. So it's a set of invertible n cross n matrices with rational entries. So of course it's a group in itself. And is it a subgroup of G? So yes, anyone?
Yes, sir.
Good, Pranjana. So what's the reason? Let's say it is.
So again, the identity element belongs to H, and for every element belonging to H, the inverse also is a rational matrix. So the inverse also exists in H. So it's a subgroup.
Okay. Why is it a rational matrix? Because the inverse will be having entries as the cofactors, which are just the product and sum of the rational numbers. And while calculating inverse, we will be required to divide the matrix of the cofactor matrix with the determinant, which is also a rational number. So consequently, at each entry, we will get a rational number, right? So you're right. Again, H is closed under matrix multiplication, because in matrix multiplication, each entry will be just product and sum of rational numbers, which is again a rational number. Closed under matrix multiplication. Let me write like this. Why is it so? Since product and sum of rationals is again a rational. Right? So it's closed under matrix multiplication, and identity, of course, belongs to GLNQ. And the third is H is also closed under inverse, right? So I hope it is clear to everyone. If you have
Sir,
any
one
doubt,
doubt.
yes.
So when we say general linear group, the operation multiplication is automatically assumed, is it?
Yes.
It's not addition or anything, only
No,
multiplication.
see, GLNC generally denotes the group of invertible matrices with multiplication. So you are right, it's already kind of assumed.
Okay, sir. Thank you.
If it is not mentioned, then it is generally assumed. If it is MNC, then the operation can be anything. Means then one has to see that what's the operation, is it a group or not. But this word invertible, this is already with respect to some operation, right? To talk about invertibility,
Sir.
we should have some group operation, right?
Yes, sir.
So by convention, this invertibility is with respect to multiplication.
Okay, sir.
Otherwise, the group of all invertible n cross n matrices would be M and C, right? Not GL and C.
Okay, sir.
है ना? Okay, good. So, what about the third one?
Sir, I have a doubt.
Yes.
So does this mean that the matrix doesn't have zero anywhere? Is this what the group is denoting? I'm unsure what
GL and C. Which group? GL and C?
Yes, sir. So does this mean that every entry is non-zero?
No, not needed to be non-zero. Only the determinant should be non-zero, right? For invertible.
Yes, sir. So here it's written that G is the group of non-zero complex numbers under multiplication. So
C.
what?
Okay. Third one.
Yes.
So, so set of all complex numbers doesn't form a group under multiplication, right? Because zero is not having an inverse.
Yes, sir.
So that's why non-zero complex numbers are taken, and the set of all non-zero complex numbers do form a group under multiplication.
Oh, okay, sir.
Hmm. Okay.
But third one is a normal set, no, sir. It's not metric set. So Pragnya was asking.
The third one is
It's a normal set of non-zero complex numbers, not any matrix, no?
yes, usual set of non-zero complex numbers. It- Just the set of complex numbers. That's it.
Yes, sir. Okay.
So, will it be a subgroup of, will H be a subgroup of G? H is the subset of fifth roots of 2. So what will be the fifth roots of U? So let looks like W, but I want to denote omega. Let omega 5 be the unit root of unity. Maybe I should write be a root of unity such that the set omega 5 square, omega 5 cube, and omega 5 4 comma 1. This is the complete is the set of all roots of unity. So means it's a primitive root which generates all roots. Like maybe I can write primitive root if you understand that term better. For example, if you have a primitive fifth root also, I should write primitive fifth root of unity. Okay. So what is the primitive fourth root of unity? It's iota, because iota square, which is -1. So if I am talking about the primitive fourth root of unity, it will be iota, the complex number iota, because iota square, which is -1, iota cube, which is minus iota, and 1. This will be the complete list of roots, fourth roots of unity, right? It's a set of all. Again, I should write fifth roots of unity. Do you understand? So similarly, we can talk about the fifth root of unity, and omega 5 is the primitive fifth root of unity. Then what will be this h? H is the collection of all fifth roots of 2. So it will be just you can denote it like that, omega 5, then fifth root of 2, omega 5 square, and same. So it's a rational number, and then this is a complex number. This is not rational, and all these will be the fifth roots of unity. And why these are the only ones? Because we are in complex numbers. So any equation will have degree as many solutions as are the degree of that equation, and we are actually solving the equation x5 equal to this x raised to 5 equal to 2. We are trying to find the solutions of this equation, right? So there will be 5 solutions, and these 5 are all distinct. So these will be the solutions of this equation, and these are going to be the 5 fifth roots of 2. So you understand what is this number, right? This is 2 raised to 1 by 5. In some places, people do write like that, but we are writing like that, okay? And maybe my notation is not that much precise. So 2 is bigger and 5 is smaller. So just like we write cube root of 2 or cube root of some number, we can write fifth root of 2. It's an irrational number, and this omega 5 is non-real complex number. So is this thing clear? Why H is this set?
Yes, sir.
So definitely it's a subset of C star. C star is non-zero complex numbers. So can anyone tell now, is it a subgroup of?
Sir, one doubt. In the
Yes.
the set H you wrote, no, the last element should be simply square roots of
Yes,
5,
yes.
no W5.
Yes. Thank you, Manu. You are right. So is it a subgroup of C star?
So the identity element of C star is 1, but H does not contain 1.
Yes. So one reason is of course that one is not inside C star. Oh, sorry. One is not inside H. So you are right. What if we include so clearly H is not a subgroup of C star. Now let's take this question to another level. Is H union identity a subgroup of C star? If I just add identity to it.
But then every element wouldn't have its inverse. so that the element A times A inverse equals 1.
Okay. Is it so?
But
Yes.
I think it will have, sir, because it keeps rotating. No, if you multiply by one of the elements, it
No,
keeps
no, this
rotating on
this
that.
omega part will have inverse, but this part won't have, right? Oh no. What will be the inverse? Manu, what will be the inverse of this?
Um, that will be 1 divided by that number, sir. But
Uh,
I'm just checking 1 second, sir.
so before going to inverse, is it closed under multiplication? For inverse also you need to compose two elements, right? So is it closed under addition?
No, sir, that length will keep increasing, I think, with
Yes.
multiplication.
So is it even so it is not closed under multiplication, right?
Yeah, the modulus keeps increasing.
So the modulus will increase. You are right. So this is so in simple words, if you express this number as uh, what to say in polar coordinates r sine theta plus or simply r uh, e iota theta. Then when we are talking about the unit roots of unity, then we always have a number of like this, right? But here this mod r is not 1. So if we multiply two such numbers, say mod r e iota theta times mod r e iota phi, then we will get mod r square and e iota theta plus phi. So here this is not uh, going to be uh, of the same modulus as this number, right? Is it clear? Means so if you multiply two numbers from this set, they won't be a root of a fifth root of 2. I hope it makes sense.
Yes, sir.
Okay. So then let me just erase this part. So it is not even closed under multiplication, and if it is not closed, there is no point of like asking inverse, because for inverse also you need to see check the closure. So, but you are right, inverse won't be there. So it is still not a subgroup of uh, C star. So this is such a bad subset that it satisfies no property of being a subgroup. Neither identity is there, nor it's closed under uh, the multiplication, and nor it contains the inverse. So it's one of the very bad subset of C star in terms of sub consideration to be a subgroup. Okay. So what about the fourth one? SN is a symmetric group on n letters, and H is a subset of odd permutations. So in class, I think in lecture notes, you have already uh, got familiar with the symmetric groups. Yes, fourth one is G is Sn and H is uh, set of all odd permutations in Sn. Okay. Again, the same question, is H a subgroup of G?
Sir, what does odd permutation mean?
Okay, so is it not defined in class? So you guys are familiar with that cycle notation of uh, permutations? So in lectures, like these are defined as uh, bijections on a set of size n, right?
Yes, sir. It's a
So
permutation group, basically. Yes, sir.
so let me just first try to define odd permutations. So we know that Sn is the group of all bijections on a uh, set of size n, right? So let this set we can consider to be just numbers from 1 to 8, 1 to n. This set be uh, S, which contains 1 to n many letters, right? So Sn will be just all bijections from this set to itself, right? Now, what you can do, so let's understand with an example. Say f is a function from S to S, sending maybe 1 to 4, or we can take a small example, say for example n equal to 6, 1 to 4, 2 is mapped to just do some notation like that. So 1 is mapped to 4, 2 is mapped to say something 5, and maybe 3 you can map to 2, and 4 maybe 1, 5 is mapped to what is remaining 3, 6 is fixed. Okay, so you can see some cycle pattern in that. So what I mean by that, so this can also be written like that: 1 maps to 4, 4 maps to this 1, right? So you're starting from a point and then coming back to this point again because it's a bijection. So such cycles will always exist. So 2 is mapping to 5, right? Now 5 is again mapped to 3, and then 3 comes back to 2, right? So again you are starting from 2 and coming to 2, and 6 is already fixed to itself. You could have started with 5 also. So 5 maps to 3, 3 maps to 2, and 2 maps to 5. So again from 5 to 5, you have got a cycle. So such cycles can be represented by this notation. So we denote it like that: 1, 4. That means 1 is mapping to 4, and then 4 is again coming back to 1. And this also one can denote like 2, 5, 3. So 2 is mapping to 5, 5 is mapping to 2, and then 3 is coming back to 2. So it's known as the cycle notation. And 6 is fixed, so we will just denote it like that. Okay. So F is nothing but can be denoted by this cycle symbol like 1, 4, 2, 5, 3, and 6. Right? So this notation you understand. 1 is mapping to 4, 4 is mapping to 1, 2 maps to 5, 5 maps to 3, and 3 is coming back to 2, and then 6 is mapping to itself. Is it clear? You can express such a bijection on n symbols by this cycle notation. I hope it's clear.
Yes, sir.
So such a notation
Yes,
is
sir.
known as disjoint cycle decomposition of F. So as the name suggests, disjoint because all cycles here are disjoint, right? And cycle decomposition because we are decomposing a function in terms of these cycles. Now, what is an even and odd permutation? So, even permutation. So first of all, let me define an even length. I think directly I can define even permutation and odd permutation from here itself. Even permutation. So, a permutation which contains even number of even length cycles. So this I will be denoting by DCD, right? I don't want to write it again. Disjoint cycle decomposition will be just denoting by DCD. So permutation which contains even number of even length cycles in its DCD, right? And so point to note is there is no restriction on, note that there is no restriction on odd length cycles. They can be even or odd, anything, but the even length cycles should be of even number. Clear? And odd permutation is same definition works. It contains odd number of even length cycles. A permutation which contains odd number of odd number of even length cycles. So again, odd cycles are not playing any role, and in its DCD, short cycles are not playing any role in the definition, right? Now here you should ask 2-3 questions. First is, what if we express, so we have seen that for this function also, there can be
Sir, one
multiple.
doubt.
Yes, Manu.
Sir, what do you mean length of the cycle?
So length of the cycle is how many elements are there in this cycle.
Okay, so in this case, 2, 3, and 1.
Yeah, so it has it's a length cycle of length 3.
That is an odd cycle.
Cycle of length. So it's an odd cycle. Very good.
Okay, sir.
So as Manu pointed out, F above is an odd cycle because it has one cycle of odd permutation. It's an odd permutation. Uh, because here there are two odd length cycles, but we don't care about them. We are just worried about the even length cycles. There is only one even length cycle, so it will be a odd permutation because the number of even length cycles are odd. So if you are more interested uh, in this, then you can read more about permutation groups, and then you will actually see why these definitions are like that. So it's not just this even number of even length cycles is contributing to this to the definition of even permutation. There is more fundamental thing which is known as transpositions, and even permutations are just the permutations which can be written as a product of even number of transpositions, and odd permutations are those permutations which can be written as an odd number of transpositions. So there is no need of even length cycle on odd length cycles. So, but for that, something more needed to be explained. But for the time being, I am skipping that part. But if you are interested, then you can see the definitions of even permutations and odd permutations in terms of transpositions. So transpositions are just length 2 cycles. So this is a transposition, for example, right? So, but here we are having a transposition, a length 3 cycle, and a length 1 cycle. So you can write every permutation as a product of transpositions, but then you will lose this disjoint part. Okay, so there are two ways to read this theory. First is in terms of disjoint cycle decomposition. Second, as a product of transpositions. Okay, so I have explained the definition in one way. If you are interested, you can read the another definition, and then interesting exercise would be to see that both the definitions are equivalent, and then also you will realize why in these definitions these odd length cycles are not playing any role. Okay, so it's an interesting exercise. You can see. So is this clear? Maybe we can see some examples. So what is your favorite number? So that we can consider SN. Don't tell a very big number like 1 lakh or 2 lakh. We won't be able to write that much permutations. So anyone?
Sir,
What is your
3.
favorite number? Huh?
We can start with 3, sir. Simple.
3. Okay. So in S3, uh, so mm, you have to answer me. I am writing some permutations. Say sigma is 1, 2, 3. Sigma 2 is just identity permutation which fixes everything. And sigma 3 is 1, 2. Sigma 4 is 2, 3. So what are odd? and even permutations.
Sir, in sigma 3, we wrote 1, 2, but 3 is missing. So that means it is just identity, like 3 points to 3. Yeah.
Yes, so very good question. So sigma 3, we are writing just 1, 2. So in usual practice, we don't, so this is same as 1, 2 and 3 is fixed. So those numbers which are fixed, we don't really write them because again, it's understood by convention. So we can simply write this like that also. Just write 1 is fixed. People will understand that, okay, 2 and 3 are also being fixed because they are not mentioned. Okay.
Oh, okay, sir.
So now
Since
others can also speak, na?
sigma 1 and sigma 2 are even permutations, and sigma 3 and sigma 4 are odd permutations, right?
Very good. So uh, sigma 1 and sigma 2 are even permutations. I hope you are also getting the logic behind it. So it has no even length cycle. It also has no even length cycle. So 0 is also considered to be an even number. So 0 number of even length cycles. So it's an even permutations. And sigma 3, uh, this sigma 1, sigma 2 are even permutations, and sigma 3, sigma 4 are odd permutations because they both have one even length cycles, right? Okay, we want to go a bit higher. Maybe let's go to S10. Take a bit jump. What about these permutations? I'm writing 1, 2, 3. That means all others are fixed. Okay. So what are even and odd permutations? First one.
First one is even. Second one is also even.
First one is even. There are 4 uh, uh, even length cycles. Second one, this is
Is also
okay,
even.
right? Third one,
Odd.
odd. Anyone else except Pranjana?
Sigma 4 is odd.
Sigma 4 is odd. Good, because there is one even length cycle. Okay. So, see, one point you should always see that we need disjoint cycle uh, decomposition to say whether it's even or odd, right? If it is not disjoint, then we can't say anything.
Means, sir, 1, 2, 3, 4, 5, 6, 7, 8 up to 9, 10 we write that we can't say anything.
No, all these are disjoint, written in disjoint cycle decomposition, right? There are no two cycles which has a common symbol.
Okay, okay.
So the point is disjoint cycle decomposition. is needed to check whether a permutation is even or odd. Now, what if you are not given a disjoint cycle permutation? For example, what if I just write sigma is to be 1, 2, 3 and maybe 3, 6, 8. Yeah, 3, 6, 7. This is not disjoint, right? Can we say anything to these permutations? Can we still say anything? The previous method failed here, right? Because that is for disjoint cycle composition. But in most of the problems in mathematics, what we do, if we learn one technique, then those examples which don't fit into that technique, we try to bring those examples to the technique that we have learned, right? So it is not disjoint cycle decomposition, but we know that what these cycles mean, right? So this cycle mean 1 is mapping to 2, 2 is mapping
Sir,
3.
one doubt, sir.
Uh,
But this is not a set of bijections, no, sir. This is 3 is pointing to 1
right.
and 3 is pointing
So
to 6
this is
also.
not a set of bijection. It's a product of two bijections. So this is one function f1. This is another function f2. So f1 and f2 are two bijections. So good, you are getting things. So these two are bijections, and then this notation means sigma is a composition of two bijections. So now how to obtain the resultant composition? So here 1 is mapping to 2, 2 is mapping to 3, and then 3 is mapping back to 1. Here 3 is mapping to 6, 6 is mapping to 7, and 7 is again coming back to 3. So there are actually two bijections, and we are trying to get a composition. So let's start from, so usually we start from uh, right to left. So here 3 is mapping to 6 under F2, but in under F1, 6 is not mapping to anywhere, right? So as a resultant, we will write 3 is mapping to 6. Then 6 is mapping to 7 under F2, but here 7 is not mapping anywhere. So 6 will be mapped to 7. Now 7 is mapping to 3 under F2, but we also have F1 here. So, and F1 maps 3 to 1. So resultant is 7 is mapping to 1. So why this is coming? This is because 7 is mapping to 3 by F2, and then 3 is getting mapped to 1 by F1. Okay. There are two uh, compositions, two bijections, and as a resultant, 7 is getting mapped to 1. Okay, this is a tricky part. Again, if you take start with 1, 1 is not here. So this bijection doesn't do anything on on the symbol 1, but this is mapping 1 to 2. So 1 will be mapped to 2. And here 2 is not mapping to anywhere. 2 is mapping to 3. So 2 is mapping to 3. So we can close the cycle, right? We will close the cycle when the number we started with is coming. Now this is a disjoint cycle decomposition, right? This is in disjoint cycle decomposition. So for this, now we can say that it's an even permutation. Is this clear, or I should explain one more time? So for this example, the notation is containing two symbols at cycles. So this kind of notation suggests that both of them are individual bijections, and the sigma is a is a resultant of their composition. So we try to obtain the resultant composition. So we start from right to left. In some books, it's from left to right, but generally we start from right to left. And so we will start looking at the image of 3, or you can start from any number in the rightmost cycle. Okay. So we start with 3. 3 is mapping to 6. So we map 3 to 6. Now where we left, this is 6. So we will start from this 6 and then start looking at its image in the rightmost cycle, and then to the second cycle. Then we will get 6 is mapping to 7. The tricky part is 7, because 7 is mapping to 3, and then 3 is also present in this cycle. So we will see that 3 is mapped to 1. So the resultant will be 7 maps to 1. Okay. And similarly, we will see 1 and 2. So let's see one more example. So now sigma is say 1, 2, 3, 4, 5, 6, and 5, 2, 7, 8. So the question is write sigma in disjoint cycle decomposition and determine. So at some books, they also call it determine its parity. So what is this parity? Parity means it's even or odd. Okay. Yes. Who's going to help me?
Sir, I can try.
Yes.
So we will take the last part, that is 7, 8, and take
You
the
can
first
also,
element.
one thing I want to mention, you can also start with any symbol you want. No need to be the rightmost part, but for whatever symbol you start with, you have to start looking from the rightmost side. So if you can start with 1, but you need to see what is the rightmost cycle in which 1 is present. So if you start with 1, then you can directly come to this cycle, because 1 is not there in all these 3 cycles. Okay.
Okay, okay. So
So
for example, 2 is there in the first and the third, but I have to take the 5, 2, 1. That's what you say.
yeah, if you're starting with 2, then you need to first see where 2 is mapped with and so let's start with 2 itself. That will clarify your doubts. So you start with 2, then you have to look at this cycle. Here 2 is
2
mapping to
goes
5.
to 5
Now
and
this cycle is done. Now you come to the cycle which is right to it. This one. Here 5 is mapped to 6, right?
yes, sir.
So now you have the 6 in number in your hand. Now 6 is not there in this cycle, right? So you will write 2 is mapping to 6. So this is coming as the outcome of 2 mapping to 5, 5 mapping to 6. Okay. Now you have to start with 6. Once you have 6 here, now you have to start with 6, because you need to see where 6 is mapping. So 6 is not here, 6 is not here, 6 is here, and 6 is mapping to 4. Then 4 is not here. So final outcome is just 4. Now rest you try to complete. What should be the next number I should write?
Sir, can you explain once again, sir?
So we started with 2. So the rightmost cycle in which 2 is present is this 5, 2. So here
Yes,
2
sir.
is mapping to 5. We won't stop here. We will see if the 5 is there in other cycles which are right to this cycle. So in this cycle, 5 is present. So here 5 is mapping to 6.
Right to the cycle or left to the cycle, sir?
Sorry, left to the cycle. We are going from
Okay.
right to left,
Yes.
right?
Okay.
So uh, we are composing, right? So now we need to see where 5 is mapped. 5 is mapped to 6, and then 6 is not there in this cycle. So the final outcome is 2 is mapping to 6. Same thing we will do with 6 now, because now we have to see where 6 is mapping. So 6 is not there in this cycle, the rightmost one. It is not there in this cycle, but it is there in this cycle. So this cycle maps 6 to 4, and then 4 is not there in the cycles which are left to it. So the final outcome is just 6 is mapping to 4. Okay.
Okay, sir.
Now tell me what number should
But
come.
4 is again mapping to 5, no, sir?
4 is mapping to 5. Good. And 5 is not there in any other cycle which is left to it. So 4 will be mapped to 5. What about 5?
That will end there, that cycle.
Uh, what will be the final image of 5 under sigma?
Or 2 only, no, sir?
No. 5 is mapping to 2, and see if 2 is there in any of the cycle left to it.
2 is again mapping to 3, right?
Yeah.
3. Okay.
So 2 is again mapping to 3, but 3 there is no cycle left to it. So 5 will be mapped to 3. So this is 5 mapping to 2, and then 2 is mapping to 3. What about 3?
Going to 1.
3 goes to 1. Then where 1 goes?
Back to 2, so it ends there.
So it ends there. Still there are symbols remaining in this permutation.
Yes, sir.
So we need to again open a cycle. And what are the remaining symbols?
7, 8.
So you can start with anyone. So I'm starting with 7. Where 7 get maps to?
8.
8. And where 8 maps to? 7. So it will
7.
come as it is. Okay. So is it a even or odd?
Even, sir.
Even side. Even permutation. Okay. Now all these things are a separate topic. Maybe it may come to the later lectures, or if you are interested, you can read permutation groups as its own. There is a vast literature available, and also there are many open research problems concerning these groups. So they constitute a very crucial area of group theory, and there are results like any group you can see as sitting inside a permutation group. So any finite group, whatever finite group you have, uh, you can see that group sitting inside a permutation group in some sense. So that group is can be seen as a subgroup of a permutation group, whatever group you have. So permutation groups are very important in group theory. So there have been very vast literature available for these groups. So definitely we are not going to discuss them. One more thing I want to mention, that this you can permute these symbols without having any impact on the permutation itself. So this is same as 2, 3, 4, 1 cycle permutation, and then this is same as 3, 4, 1, 2, and which is same as 4, 1, 2, 3, because it won't affect the final outcome. Okay. And also you can you can change the order of disjoint permutations. So 1, 2, 3, 4, 5, 6, and say 6, 7, 8. This is same as 5, 6, 1, 2, 3, 4, and 6, 7, 8. So disjoint cycles commute. You can check that. Disjoint cycles commute. So that's why the order doesn't matter. Here we started with 2. You could have started with 1. And if you would have started with 1, then you would have got the permutation. So let me just say some more things. So this is because cycles can be presented in many ways, or if it is clear, then I won't write. Okay. So basically, you can cyclically permute the numbers. It won't affect the final permutation. So the question now is, what if I have started with symbol 1 instead of 2 in the above example? In the above example, we started with 2, and what if we have started with 1? See, we are trying to express the same example by starting from 2 different points. Now, if this theory is consistent and useful, then we should have got the same output, right? Otherwise, there will be inconsistency depending on from which point you started. So it's that I leave it to you. So if you would have started with 1, directly by looking at the answer you got in the previous case, you can predict what will be the representation you have got. So if you would have started with 1, you would have get the same cycle, but the cycle will be starting from 1. So you can
1,
write
2, 6, 4.
this cycle as 1, 2, 6, 4, 5, 3, right? So we just cyclically permute this 1, 2, 6, 4, 5, 3. So which is same as the previous one, but just we are starting with 1. So if we start with 1, we again cyclically permute it. 1 going to 2, 2 going to 6, 4, 5, 3, right? And 7, 8 will come as it is. So the order in which you started with doesn't matter. You are getting the same output because we have seen that you can cyclically permute and still the permutation remains same. Okay. So all this was not planned, but it's good that you asked the question and we see all this theory. Now, can we come back to our question on subgroups if there is no
Yes,
other
sir.
doubt?
Yes, sir.
Okay. So it says if Sn is a symmetric group on n letters and H is a subset of odd permutation, is H a subgroup of G?
Again, the identity doesn't belong to
Very
subgroup.
good.
It's
The simplest way to discard an example is to check whether identity is there or not. So is the set of odd permutations forms a subgroup of Sn. And as Pranjana pointed out, identity is not an odd permutation. It's an even permutation. So one thing is clear, a permutation is either even or odd, right? So It's in fact a even permutation. So it's not going to be an odd permutation. Also, product of two odd permutations is an even permutation that you should check. Product of two odd permutations is an even permutation. So
Sir, identity is an even permutation also.
right, so it's not an odd permutation. That's what I'm writing.
Oh, sorry, sorry. Okay.
So product of two odd permutation is an even permutation that you should check. Can someone quickly tell me why? Just follow the definition. One problem is when you
Because you
take the
add two cycles, it goes into the other cycle and it becomes an even.
so whatever definition we read, we have mentioned above, we we focus on the disjoint cycle permutation, right? So if we are taking the product, then that the resultant may not have a disjoint cycle permutation, right? But if you see the other definition that I just spoke but didn't write, that an even permutation is a product of even number of transposition and an odd permutation is a product of odd number of transpositions, right? Now, if you take the product of two odd permutations, then you will have two permutations with odd number of transpositions. So odd and odd will give you even. So the resultant will be an
That common element will become removed, sir. So maybe the total cycle becomes like an even
that
number.
not necessary. See, you won't be able to directly say it.
Okay, okay, sir. Okay.
That's why I'm telling you, you can leave that part if you're not familiar with the second definition. Second
Hmm.
definition is easier to say, but it will
It's
again take
something
some
more
time.
abstract than.
Ha. So for the moment, you just believe me that product of two odd permutation is an even permutation. If you are interested, then you can see the definition through transpositions. It's not difficult. It's not at all difficult. The more difficult things we have already seen in examples. It's just that I don't want to state so many definition in a single class. Otherwise, you would be bored and you won't get the motivation to continue this course. So for the moment, I think these much definitions are enough. You just believe that this is the fact. So it is not even closed under uh, this take product thing. Third thing, you can directly check inverse of a odd permutation, odd or even permutation is an odd or whatever you started with even permutation. Okay, should not write or. You understand this notation, right? So that means that if it is odd, then it will remain as odd. If it is even, it will remain as even. Because if you take the inverse of a permutation in disjoint cycle decomposition, then you can observe something, and that observation will help you to conclude this. So this also I am leaving it for you to check. So under inverse, it is closed. But inverse will make sense only when identity is there. The first two property doesn't satisfy, and you can say that it's closed under inverse and the identity is the group identity. Okay, so I hope this example is clear. If it is, we can move to the next one. This is also not a subgroup. What about the fifth one?
One is a subgroup.
It is a subgroup. Can you just say why?
Again, 0 belongs to H, and for every element of form A plus IB, there exists inverse where it's minus of A plus IB. It also belongs to H, so
It's also
and it's
closed,
closed.
right? So 0 is there. 0 belongs to H. And closer you can check. Because if you take two numbers, say A plus iota B, uh, again plus C plus iota D. So I can just write in one line A plus iota B. And then again, if you take plus with C plus iota D, it's just A plus C plus iota times B plus T. Right? So this is of the same form. This again belongs to Z, and this again belongs to Z. So this is again inside H, right? So closure is there. It contains elements of the form A plus iota B, A and B inside set. So closure is done. Inverse also you can see the inverse of A plus iota B is minus A minus iota B. So inverse will also be there. So I just leave it like that, no? You can verify the details. What about the sixth one?
Sir, one doubt. This set called that Gaussian complex numbers or something?
Yes, set of Gaussian integers.
Go- Gaussian integers, sir?
Some people say it like Gaussian integers.
Okay, okay. Okay, sir.
Gaussian complex numbers also people do say. There is also a version of it for fields which are not complex. But again, I don't want to confuse you more. So this iota is very specific. So A and B are elements of Z, and for fields that are not C, there are something called degree 2 extensions of in field theory. And so with respect to any degree 2 extension, one can define a set which is similar to this set. So just to give some motivation, but don't get diverted from the question. Your question is very nice. So yes, it is known to be the set of Gaussian integers, or at some places to be the Gaussian complex numbers also.
Okay, sir. Thank you.
Okay. What about the sixth one?
H does not contain the identity.
You are very much behind this identity thing. Good, but it is very nice that this thing is working every time. So, as Pranjana pointed out, identity is not there. So,
Also closed, not closed, sir.
not
You add
closed
A
as
plus
well.
I, A plus I, 2A
So,
plus 2I.
closure is also not there. And so, this is not a subgroup. What about seventh? So, one thing I can say, identity is there.
It's also closed,
Also
and
closed.
inverse exists for every
Inverse
element.
axis. Very good. So it's a subgroup. Aha. Now eighth one. Sn is the symmetric group on n letters, and H is the subset consisting of two cycles. So now you know what is a two cycle? A cycle of length 2. And n cycle means a cycle of length n. It's a subset which contains all two cycles.
So it is even but exactly two cycles, sir.
So H contains exactly two cycles. Pranjana, I am expecting an answer from you. You can use your favorite trick.
Yeah, again, identity doesn't belong.
Identity is not there. And Manu, what about closer? You are a fan of closer, it seems.
Um,
Inverse is there. If you take inverse of a cycle, then it will again be a cycle of same length.
so it's closed only, you know.
Check. Mm, let's see. Eighth one. G is Sn. Meanwhile, you check if it is closed. H is the set of all two cycles. So, of course, identity is not there. And
Oh, sir, product of two even permutation is odd. Is it, sir?
product of two even permutations is again even permutation. So product of odd number of even permutation is odd. So whenever you get confused in this, you just remember the second definition, because that is free from the disjoint cycle composition thing. Maybe I can just write it
You
some.
mean identity? We have to just remember easily.
I couldn't get.
No, sir. When such questions comes, you said it's easy to remember the identity part and
No, the second
etc.
definition part that says that there is some transposition, and even permutation are product of even number of transpositions, and odd permutations are product of odd number of transpositions. So if you are taking an odd product of odd permutations, that means you will be having odd number of transposition in total. So uh, so that means you will be having a odd permutation. Maybe I can just write it somewhere so that.
Yeah, okay, sir. Yeah, that will be helpful. It's a little confusing at this. I mean, for entry level, I think. I don't know.
So I can just write. So note that first is uh, product of even number of even permutations here I can use this trick, even odd trick. So even number of even permutations is a even permutation, and if you are taking a odd number of product of odd number of even permutation, it will be an odd permutation, right? So this notation you understand, right? For even you have even, and for odd you have odd. Okay. And second is product of even number of odd permutations, also it is even. Whenever you are having a just a minute, maybe I'm missing something. Oh yes. So in case of even permutation, the number doesn't really matter. Whether you are taking an even product or an odd number of cycle permutation in product, you will always get an even permutation. Because odd times an even times an even, they are always even number, right? The problem is when you are having a odd permutations. So even number of odd permutations is an even permutation, and odd number of odd permutations is an odd permutation. Is it clear now? So when you are taking product of even permutation, it is always going to be an even permutation, no matter whether it's an uh, even number of product or odd number of cycle, odd number of permutations in the product. But when you are taking product of odd permutations, then you need to see whether it's an even product or an odd product. The resultant will depend on that. So in this example, we are taking two cycles. So two cycles are odd permutations, right? Because two cycles have only one element in the DCD. One even cycle in the DCD, right? So if you take the even product, then it will be a even permutation. If you take the odd product, then it will be an odd permutation. But there is a simpler way to see this through example. So what about this? This is a two cycle. This is a two cycle, right? What will be the resultant?
1, 2, 3. That is even.
1, 2, 3. Very good. So this is not a two cycle.
No, sir.
It's a three cycle, right? So it's not even closed. Any doubts?
So if it's not closed, we can't write like that, no, sir. We don't know how to. If this 3 doesn't point to 1, how do we write it, sir?
Oh, I'm doing some mistake. Who is going to, maybe some other way to write, but it should be a three cycle. So 1 is going to 2, that is fine. 2 is going to 3, and 3 is not going anywhere. 3 goes to 2 and 2 goes to 1. It is correct, right?
1 to 2, 2 to 3, and then 3 to 1 you should add.
No, we will start from right to left. 2 going to 3, 3 is not here, so 2 will be go to send to 3. 3 goes to 2, 2 is going to 1, so 3 is going to 1. 1 goes to 1 is not here, 1 is here, so 1 will be mapped to 2. Is it okay?
Yes, sir.
So 3 goes to 2 and 2 goes to 1.
So 3 is going to 1, right?
Yeah, so we should write 3 to 1, sir.
So that cycle means this means 3 goes to 1. This is same as writing 3, 1, 2 or 2, 3, 1. You can use any way to write. Here I am starting with 1, so I'm writing 1, 2, 3. If you're starting with 3, then you can write 3, 1, 2. But all these are same, right?
Yes, sir. But can you just once again do that, sir? That from left to right. 2 goes to 3 and 3 goes to 1.
No, 3 is not here, na. 2 goes to 3 and that's it. 3 is not here. So 2 will be sent to 3 only. You're starting with 2, right?
Yeah, so 2 goes to 3 and
That's
3
it.
will again go back to 2. No, sir, in the composition left side LHS.
So this, no, I'm writing that this permutation is equal to this. I'm not taking product of all three.
Okay.
So here 2 goes to 3, and then we need to see this cycle. This cycle doesn't contain 3, right? So final outcome for 2 will be 3. So here 2 is going to 3. Then 3 is mapping to 2. 2 is also there in this cycle. So 2 is mapping to 1. So for 3, we have the final outcome to be 1. So 3 is mapping to 1.
Yes,
And
sir. Correct. Correct.
1 is,
Sorry, I got confused. Yeah. Sorry, sir.
is it okay?
Yes, sir.
No, it's fine. You are looking, seeing this thing for first time. So it's, this kind of confusions will arise. No issues. So it's not a subgroup. Product of two cycles need not be a 2 cycle. And also, as Pranjana pointed out, uh, identity is not there. So, okay. What about the next one? So G is the set of real numbers, which is also an additive group. H is a subset of real numbers whose square is a rational number.
This is not closed tensor addition, so it is not a subgroup.
What about identity?
Identity exists, but then closure.
Identity is there, but it's not closed, right? So I can just write here. I don't want to go back again and again. So I'll just write here. So identity is 0, right? So 0 belongs to H, but what numbers we should take? Maybe 1 and 4. Both are there inside H, but 1 plus 4, that is 5. This is not inside H, right? Oh, maybe we are doing some mistake. Is the subset of real numbers whose square is a rational number. We are doing the other
So
way.
we can take root 2, sir. Root 2, root 3.
Root 2 and root 3. So I was just thinking in another way, whose square root is a real number. So this also vanished. Wow. So 0 is there. So root 2 and root 3 is there inside H, but root 2 plus root 3 does not belongs to
False.
H. Good, Manu.
Yeah, because its square is not a rational number.
Its square is not a rational number. Its square will again be a rational number. And then last one, G is the set of real numbers, non-zero real numbers, and uh, under multiplication. And H is a subgroup which contains all squares.
Sum of two squares is not a perfect square.
No, multiplication.
Sorry, multiplication, sorry.
So see, 0 is there. Now if
0 is not there, no, sir. It's non-zero.
oh, here the multiplicative identity is 1.
1.
Thank you. So 1 is there. 1 is a square, right? 1 is a square of itself.
Yeah. Yes.
And if a square and b square belongs to H, then what is a square times b square? We are inside real numbers, so that will be just ab whole square, right?
Yes, so closure is satisfied.
It's again inside H, and inverse also you can check. A squares inverse is just a inverse square. So this will again be inside H. So this is also true. Is it okay? Or any doubts?
No doubts, sir.
You can see all parts once. If there is any doubt, then let me know. We can discuss them here. I will just try to take the second question till then.
Sir, one doubt. These classes which you record, will that be put in YouTube or anywhere, sir? Generally in NPTEL and in this class particularly also.
So they must have shared some link, right? They haven't.
Link where we can see recordings.
There should be some lecture notes also. They have not shared it till now, I guess. They should have shared. Suddenly they put it on the course webpage.
Okay, okay. So all these problem solving sessions, they record and put links there.
There is a oh, it's there. It's there, right? If you just go to the page, then there is uh, uh, section called as problem solving session July 25. There you have uh, problem solving session recordings.
Okay, sir. Thank you. And similar to other, similar with other courses also. It's a standard practice, no?
It's a standard process. It's a standard process.
Okay, sir. Thank you.
So I keep, so maybe if you just, because you have asked, I can just share that page with you and you can see. Uh, this is visible, right? The course web page.
Yes, sir.
So if you go here, then in the course outline part, there is this problem solving session. You just click it. Then you have this problem solving session recording. If you click it, then it shows click here to view the problem solving session lectures. If you click it,
Okay.
Excel sheet will open. You can see the Excel sheet.
Yes.
Yeah. So this, so I will be updating these YouTube links each week. Once the class is over, maybe in a day or two, I will do. And this
Sure.
folder is fixed. It will be containing the notes, lecture notes. Okay, so this is the last.
Which you are used marked now, no? You are like
Whatever
scribbling whatever that is.
right. But I strongly recommend that you attend classes because as you are seeing that I'm developing on your inputs. So whatever doubts you have or uh, you can uh, discuss this. Otherwise, you will be looking at someone else's doubts, right? So
Yes, sir.
do attend lectures. Okay. So maybe I can reshare and okay. So if there is no doubt on question one, we can possibly move to the second question. We have some time left, so we can discuss hopefully some more. So here we need to select all statements that are true. Okay. So what are your inputs? Maybe we can start with the first part.
First seems true,
All
sir.
is true.
First seems to be
True.
true. Why?
Because 2Z, 3Z, 4Z, all like
Very good. So
NZ is
subgroups of Z are NZ, where N belongs to N. Um, even N union 0 also we can write. So
subgroups of the form. Yeah, yes, sir. NZ.
maybe This is a standard notation for nz is like set of all elements which are multiple of n.
Yes, sir.
So this is correct, right? What about the second? Every
Second
subgroup
one
of
is
Z is
also
cyclic.
true.
So what is the definition of cyclic again? I forgot.
Good point. So, although I think it's been defined in lecture,
Oh, so, okay, okay. Cyclic has a
Yes.
generator at least one.
a single generator. It has all elements of the form some a times a raised to something, right?
Okay, at least one generator. Okay.
This
Every
statement is
subgroup.
also true.
True, yeah,
Uh,
true, sir.
yes, Pranjana, you were saying something?
No, I was just saying that this statement is true.
My statement, which first or second?
And the second one.
Second one is
Second
true.
one, sir.
Why?
For n is n is the generator.
And Zn is the generator. Very good. Third one,
Third one is also true.
true. Reason?
Um, I don't know what it's supposed to be called, but then I can find the generator. For instance,
It's called
uh,
primitive
I-
root of unity, and it is of this form. E raised to 2 pi iota by n, which is uh, just if you see in complex notation, this is cos 2 pi by n plus iota sine 2 pi by n. Right? So it's a complex number and it generates all roots, is the generator. Why? Because if you take a power, say, if you take kth power of it, you will get a kth multiple of this number, 2 pi by n. So kth power will be cos 2k pi by n plus iota sine 2k pi by n. And when k is equal to n, you will get 1. You will get all uh, generators, sorry, all nth roots of unity in this way. Is it clear?
um, yes, sir.
Sir, but except one, everything are generators, no, sir?
Except one, not necessarily.
We
What if
keep
n equal?
multiplying, and because modulo, it goes
What
to
if
that
n
modulo of
equal
2
to
pi.
n equal to 4 and you have minus 1?
Sorry, sir.
So if n equal to 2, then you have minus 1 as a fourth root of unity, right? But it's not a generator.
No, I'm saying like cos k into 2 pi by n. That
Uh,
k can be anything 1, 2, 3 less than n. So all
right.
for all k they are generators, no?
No. You can take n equal to 4 and k to be 2.
N equal to 4. Okay. N equal to 4 and k equal to 2.
Then your
Oh, GCD must be 1.
GCD must be 1.
Sorry, sir.
Very good.
So all
Clear?
GCD ones are called primitive roots, sir?
All GCD ones are called primitive one roots. Primitive means the generator of the group containing all nth roots, and those generators are precisely the ones which have this k to be co-prime with n. That is
Okay, okay, okay.
what you say GCD one.
Okay, sir. Okay.
Mm.
Sorry.
Clear? Okay. Next one. The symmetric group S10 on 10 letters is abelian or not?
No, sir.
No. Why?
So what does it mean, the question on 10 letters because S10 anyway have 10 only.
Oh, so it just defines the notation S10, that's it. The question can be the symmetric group S10 is abelian.
Yeah. So it's redundant the question.
It's
Some
redundant, but just to give you information that's what this S10 means. That's it.
understood. Understood, sir. Okay, sorry.
Mm. If you know what is
I thought it
S10,
was
then
acting on some other thing,
no.
but confused.
If you are okay, then one can even write the group S10 is abelian. No need to write symmetric also.
Oh, okay, sir.
But it just to give you information that what this S10 is. Okay. Okay. Is it abelian? Pranjana, you were saying no. Can you justify?
Yes, so I can give a counter example. So suppose I have again, I don't know how to okay, so the composition of 1 2 3 and 1 2 is not same as the composition of 1 2 and 1 2 3. So it's
Composition
not
of 1 2 3 and 1 2. So what it will be?
is 1 3.
So 1 going to 2 and 2 going to 3. So 1 is going to 3. 3 is going to, so 3 is not here. 3 is going to 1. So it will be this. 2 is going to 1 and 1 is going to 2. So 2 will be fixed. So you can write it as 1 3. And all others symbols are fixed, right? From 4 to 10, everything is fixed that we are assuming. Now, 1 2 and 1 2 3, right? What it will be?
2 3.
So 1 will go to 2, sir. Then 2 in the left side will go to 1. So 1, 2 will remain independent and 3 will remain independent.
No, 1 will be fixed, not 2. 2 is going to 3 and 3 is not here. So 2 will go to 3. 1 will be fixed. 1 going to 2 and 2 going to 1. So 1 will be fixed.
Correct. Sorry. Yeah. Yes, sir.
3 going to 1 and then 1 is going to 2. So 3 is going to 2. So this is just this. So both are 2 cycles, but both are different. So yes, Pranjana, you are correct. So this implies S3 is not abelian, but S3 is already sitting inside S10. So S10 is, so Sn where n is greater than equal to 3 is not abelian. This example is very nicely picked, I will say, because it shows that any Sn for n greater than equal to 3 is non-abelian. Clear?
Yes, sir.
Because if S3 is anyway sitting inside any Sn, n is greater than equal to 3. Okay. The next one, the kernel of a group homomorphism is always a subgroup of G. So it's already done in the class. So I will omit it. Okay. Kernel and image both are subgroups. I can leave it, right?
Yes, sir.
Okay. Next one, you have a group homomorphism G1 to G2 between two groups G1 and G2. If G1 is cyclic and phi is surjective, then G2 is also cyclic. So I hope you understand what is surjective. That means each element in G2 has a pre-image. Okay. It says if the first one is cyclic and the homomorphism is surjective, then the second one is also going to be cyclic. Shall I do it for you? So let G1,
This is true, right?
yes. Can you tell me why?
I might need a minute to come up with a proof. So
You can take a minute.
um,
We have that much time. No issues.
okay.
Can you tell me what should be the generator?
Sorry, sir.
Can you tell me what should be the generator? I'm saying that let G1 be generated by A.
Oh, so the generator would be mapped to the generator of G double prime, and so
Phi of A.
Phi of A. So claim is
Oh, so the claim is phi of A is the generator of G2, sir.
yes, claim is G2 is generated by Phi of A. Now can you prove this claim? You're right, you just need a minute. It is easy. Just take copy pen, and even without copy pen, if you just think for a moment, you can tell.
so phi of A plus E equals phi of A plus phi of E, which is equal to phi of A.
From where A in E are coming?
So A is the generator and E is the identity.
But
So phi of A is same as phi of A plus E. So phi of since this is a group homomorphism, this is same as phi of A plus phi of E of the G prime.
right.
So that's same as just phi of A.
But
Sir, but the
the
operation, what is the operation, sir?
operation generally we just take product. Means if she is okay with plus, she can take, no issues.
Okay. Like star and hash or something like that.
Star, hash, anything, it's just a notation. And if no
Okay.
nothing is given, then you can take any notation. But whatever you said, Pranjana, that is correct. But does it says that every element is a power of phi A, or phi A generates G2?
This is not sufficient. But then once I know that phi A maps to the once I know that the generator maps to the generator, then I
That
can
is the
take.
point.
Oh,
That won't that's what we want to show. The generator maps to generator.
oh. So phi of A plus A would again be phi of A plus phi of A.
That is okay.
So I could just extend this phi of A power n would just be
But why everything is of this form? So you getting this, we need to show that if say some B belongs to G2, then there exists some I belongs to N, or if you're using this I for iota, then I should not use this here. Say there is some K belongs to N such that B is phi A raised to K. If you are taking addition notation, then this would come here, right? It's just that phi of A is being operated to itself K many times. So we need to show that everything is just a power of phi A. So one hint is in all your explanations, you are not using phi to be surjective. It should come into picture, right?
yes, sir. So suppose that B naught belongs to G1 such that phi of B naught equals B,
Right.
and B naught equals A power K for some K.
Right.
So now I know that phi of A power K equals phi of A power K,
Good.
which is
Good.
which
Good.
is equal to uh, B. So
You're absolutely correct. So let B naught belongs to G1 such that B is phi of B naught. Then uh, B naught should be equal to A power some J. I'm not using the same notation for some J belongs to N, and this implies uh, B naught B is equal to phi B naught, which is phi of A J, and that is phi A raised to J, right? And that's it. Clear? It completes the proof, right? So any element in G2, you can write it as a power of phi of A. So phi of A is a generator of G2. Subjectivity is needed. Without subjectivity, you won't be able to conclude this.
Sir,
That's,
what is the point where subjectivity is used here? When we write phi of B0 is phi of A or G.
so you can write every element as phi B naught. Here the subjectivity is used for this step.
Okay. Oh, so homomorphism, it is not necessary that it's subjective. We
No,
have
no,
to
no.
add subjectivity.
Yeah, yeah. Homomorphism just means that phi of AB is phi of A times phi of B. That's it.
Okay, okay. So subjectivity is not part of homomorphism.
Subjectivity is not part of it.
Okay, sir. Okay.
Okay. So, so this is also correct. I'll just have a look at it and let me see if there is enough time to discuss the third problem. So are there any doubt in the second question? Any part?
no, sir.
Okay. Mm, okay, so let me just copy paste question number 3 of assignment 2, practice assignment 2. I hope I am not discussing questions from assignment 2. That would be a blunder. Right. Okay. So this is question 3. It says if H is a cyclic group of order 10 for a positive integer n, let An be the number of subgroups of order n of G. Which of the following are correct? The question clear? So you're given a cyclic group of order 10 and An is the number of subgroups of order n of G. Then uh, you need to see which of the following statement is correct. So the first part, An is non-zero for every n greater than 1. Is it true?
Yes, sir. At least one subgroup will be there.
Huh?
At least one subgroup will be there.
One subgroup will be there for each n. So let's say I use this notation. So G is cyclic group of order 10. Na? So here we have uh, A, A square, A cube, and so on, A raised to 9. And then A raised to 10 is identity. Okay. So will it have a subgroup of orders 3?
No.
No. Why? Is A3 non-zero? So one of them is one of you is correct. So Pranjana is saying no. Manu, you want to say yes, right?
Um, I think I misunderstood the question, sir. Let me think once again. Please carry on, sir.
So you need so one of you should convince the other that the person is not correct.
I, Prajna is correct. Pragnya, I think.
Means I hope I am pronouncing your name correctly.
So my name is Pragnya.
So J is silent. It's
It's spelled that way, but it's pronounced Pragnya.
oh Pragnya. So sorry for the entire class. I was just spelling it wrong. So you should have told me. Okay, so Pragnya, uh, why is it so?
So it's just the intuition is that since this is cyclic, um, I know that A is a generator and A power 10 will give me E. And then I could take A square. Then if A square is the generator, I get of A square power 5 will again get E dash. But then, so, um, but then this is not true for A cube. I'm just trying to find a more
It doesn't means
better
that
way of
A
explaining.
cube is a generator or uh, something like that. It means that so if A3 is non-zero, then there exists H subgroup of G such that size of that subgroup is 3. That's what it means. So AN be the number of subgroups of order n of G. So if A3 is non-zero means that means there is at least one subgroup of order 3.
So suppose there is some subgroup of order 3 contains A cube. So once we know that A
Hmm.
cube belongs to
It
H,
need not contain A cube. So order 3 subgroup means it has 3 elements.
yes, sir. I'm sorry. I'm sorry. Makes sense.
Like let's say A square and E, because
So
it should
what
contain
is the possibility for H?
A square E or anything like that. A square and A7, something like that.
Then
But
H
E should be
should be
there
of
at
this
least.
form. So first of all, identity should be there, right?
Yes, sir. And then
And you can have at most 2 elements.
if you take A square, then you should have A power 7.
So if some A raised to I is there, and then the other element is you can take to be A raised to J, right? Only this is the possibility, right?
Yes.
Yes.
Now you must have inverse.
So
So either so there are 2 possibilities, and of course we are assuming I not equal to J. Otherwise, it will be 2. There will be just 2 elements. So uh, which implies AI times AJ should be identity. It cannot be AI, it cannot be AJ. If it is AI, then AJ is identity. If it is AJ, then AI is identity, right? Left cancellation rule, right? So their product should be identity because their product shouldn't be inside this set.
So J is like 10 minus I,
Uh,
if it's possible.
and both I and J are also less than 10, right? So this implies that I plus J should be identity and it is less than 10. So only possibility is it can be A10,
Yes.
right? That means I plus J has to be 10. You agree with this?
Yes, sir.
But what does this means? J is the inverse of I, right? This means AI is A raised to minus J. From here you are getting this.
Yes, sir. But
So,
before that, sir, I want to ask, closure we are already assuming, is it, sir? Like, let's say A power 2I, we are assuming it's there.
closure, so it's a subgroup, so it will satisfy all properties.
Okay, okay. So we're just checking for inverse now. We are already assuming that it's closed.
No, we are not
A power I.
assuming. We take a set H. Now we want to argue that it won't be a subgroup
Okay.
because
But this is not closed.
Yeah, this is not closed first of all. Like A
yeah,
power 2I, A power 3I, and all might not belong because it
right
has to be. Yeah.
now this says that I plus J is equal to 10. So J is just uh, 10 minus I. So this implies your H is identity AI and A 10 minus I. Okay, correct?
Okay. Yeah.
Now AI square, which is A 2I, should also be inside H.
Yes, sir.
So then again, there are possibilities. This
2I should
implies,
be either 10
first of all,
or.
so there can be two possibilities, or let's consider three possibilities.
Yeah.
A2I is identity,
Yes.
which implies A2I is can be A10. It should be some modulo 10, but as I is considered to be less than 10, so the only possibility is A10, right?
Yeah.
So I is 5. Second is A2I is AI. That means AI is identity, which cannot be the case.
Yeah.
Third is A2I is A10 minus I.
Yeah. Which is J, A power J, the
Again,
other element.
since so this will be, if I take A this side, so this will be A2I, A10 minus I inverse, that is equal to identity, right? I am multiplying with A10 minus I inverse both sides. So this will be A2I minus 10 plus I to be E. Is it okay? Just I am taking minus inside this power. So A minus 10 plus I. This will implies A3I minus 10 is again A10, which implies, or some uh, take 10 is to 10 times K. It is some power of A10. So what does this means? This mean your I is 3I minus 10 is 10 raised to K for some K, but you will see some contradiction here. So 10k plus 1, right? So 3 cannot divide 10. So 3 has to divide this k plus 1. So 3 must divide k plus 1. And I is strictly less than 10. So this 3i cannot go beyond 30, right? So this k has to be 2. Clear? I is less than 10 and 3 divides k plus 1. So this number cannot go beyond 30, and so k plus 1 can only be 3, which means k has to be 2. But if k is 2, then I is 3i is 10 times 3, which means I is 10. Clear?
No, sir, like K can be like, let's say 26, no, sir?
Can be,
Example as like 26, because 26 plus
but
1 is
see,
27.
3 I is less than 10. So what can you say about 3i? 3i has to be less than 30, right?
30. Yes.
So this cannot be, this k plus 1 cannot be more than 3. So that's why k has to be 2, right?
Okay.
So here I is 10, which is a contradiction, because I is assumed to be less than 10, right? If I is 10, then AI is identity. So the only possibility is I is 5. So this implies I is 5, and which implies 10 minus I is again 5. And that means AI and A 10 minus I is are same. So it's a contradiction because they are assumed to be different elements, right?
Okay.
Let me just explain this part again. It is bit calculative, then we will stop. So this, we take a 2 power, we take a square of AI edge. So it should be inside edge if it's a subgroup. So there are 3 possibilities. A to I is identity. That means A to I is some power of 10. But as I is less than 10, so 2i can be 2i has to be 10. That means I is 5. And second part is A to I is equal to AI, which means AI is identity, which is a contradiction. Third is A to I is same as A 10 minus I. So I will take A 10 minus I this side by taking inverse. So it will be 2i minus 10 plus I equal to identity. And it has to be some power of 10. So 3i minus 10 is equal to 10k for some k. And 3i is 10 taken common with k plus 1, and thus 3 is a prime. So 3 either divides 10 or k plus 1. 3 doesn't divide k 10. So 3 has to divide k plus 1. But this number 3i cannot be more than 30. So this k plus 1 has to be 3. And this implies k is 2, which is a contradiction since I becomes 10. So there is no choice of this I which satisfies this. So this cannot be equal to A to I cannot be equal to A 10 minus I, and thus the first option is has to be the only choice, which says I equal to 5, but that means 10 minus I is 5 again, and which means AI and A 10 minus I is same. So this set is not a uh, set containing 3 elements. It's just a set with 2 elements. So that's a contradiction. Okay. So there won't be any uh, set, any subgroup of size 3. So A3 has to be 0. Okay. So this implies A3 has to be 0. Okay. Now I leave it to you to check one thing, that checks A n is non-zero if and only if GCD of n and 10 is not equal to 1. Okay. So that means the first option is not correct because it says for every, this is already we have checked because A3 is non-zero, and so 1, 2, 5, 10, all these have GCD not equal to 1 with, oh, there is a catch. So I should not write like this. I should write if and only if n divides n, because this will n divides 10. This will the previous one would have left n equal to 1 option, but there is a subgroup of order 1, right? The singleton set identity. So it should be n divides n, not the GCD one. So this should be the correct thing. And for any n, either an equal to 0 or an equal to 1, that also you should check that if the subgroup is there, then it's a unique one. So I leave it to you. For cyclic groups, only subgroups are those which are of order n, where n is a divisor of, here 10 is the order of group, say the order is m. So a cyclic group of order m has subgroups for each divisor of m, right? And those subgroups are unique. So either an equal to 0 or it is equal to 1. And of course, if n greater than equal to 11, a cyclic group of order 10 or any group of order 10 cannot have a subgroup of order 11, right? A subgroup cannot have more elements than the group itself. So this one is also wrong. Okay. So only this part is left for you. Is it clear? You are here or gone?
Yes, sir.
You
Yes,
just
sir.
check the details. If you find any difficulty, any doubt, then you can let me know in the next class. We can start from here if any difficulty arises. Okay.
Okay, sir.
Okay, sir.
Okay, then so I can stop sharing, I guess. If you have any doubt, then you can ask. Otherwise, we can stop the meeting here.
Okay, sir.
Okay, so we will meet next Tuesday from 6 to 8. Okay.
Okay, sir. Thank
Thank
you.
you very much, sir.
Okay.
Thank you, sir.
Bye.